this computer. All right, it's recording.
All right, cool. So hi guys, my name's Joshua Schember. Today we're going to be doing some sketchy mathematics where we're going to make some bad estimations, a few guesstimates just to make sense of some absurd situation. And so on that, today's question that we're going to be tackling, what would happen if you had a mole of moles? So for anyone that is not aware, what is a mole? Well, a mole is also called Avogadro's number. It's 6.0221409 times 10 to the 23rd. I tried to make it as accurate as possible. Most people just abbreviate it to 6.022 times 10 to the 23rd. And it measures an amount of something, approximately 6.022 times 10 to the 23rd of those things. A mole is a small rodent. It lives most of its life underground. And we're going to be using the species, the Altai mole, which is the largest species because it's more fun that way. And you guessed it, it lives primarily in Russia. So the units that we're going to be sticking with, when I did how to slap a chicken, there was a little confusion on the units, and I think that's where some of my math went wrong. So today, everything will be in terms of meters, kilograms, and pascals.
The real units.
Real units, yes. We're trying to stick with standard as much as possible. But, yeah. So, the givens that we're working with today. The mole mass. So the average mass of one of these moles is about 0.142 kilograms, or like, I think it was like 5 ounces or something, 6 ounces. The average mole length is 0.17 meters. I couldn't find an actual volume, so we're going to have to compute that ourselves. Earth's mass has been found to be 5.972 times 10 to the 24th kilograms, and its volume is about 1 trillion kilometers, or 1 quadrillion meters cubed. And so we're working with very, very large numbers for that. And those are just for comparison to the amount that these moles will have in mass. So now we're going to move to the whiteboard so we can actually start doing some calculations. So make sure that works. All right, everybody can see this well-ish? All right, and you can still hear me, right?
Yeah.
Okay, awesome. So the first thing we're going to need to do is compute the volume of 1 mole. Everybody can see that well? Do I need to write bigger?
No, this is great. This gives me some feeling for like what my students are.
Yes. All right, so when we found with a mole, the length was 0.17 meters, and that's from rump to nose. And so what I did to approximate the volume, I looked at moles as basically a pill shape. So it's like, a cylinder with 2 half circles on each end, and that entirely has a length of 0.1 meters. So from that end to end is 0.17 meters. So to find the volume entirely of the mole, you can cut the 2 hemispheres of the ends off and make that 1 sphere. And then you can just take the volume of that with a regular cylinder. That just makes it a lot easier.
Mm-hmm.
And so what I found with the width of a mole, I kind of had to estimate it by looking at pictures. They look about half as wide as they are long. So yeah, the diameter of this sphere as well as the diameter of this cylinder is going to be half of the 0.17, which I didn't write it down, but it's like, do some quick math. Okay, so the diameter is going to be 0.085, and the radius, which is what we're going to be mostly focused on, is 0.0425. So 0.0425 meters is going to be our radius. All right, so now keep going down. So when we're looking at the sphere, the volume of our sphere, hey, Joe's here, nice. Wait for it. Hi, Joe.
Hi.
Nice. All right, so the volume of our sphere equals four-thirds times pi times our radius cubed. And so that, I'm not going to try to do all that, but the volume of our sphere is 0.0075 meters cubed. So that's pretty small. So if you have paper, write that down. If not, I'm going to move on and do the cylinder and then add them together. I've got it all on paper here, so I don't really need to keep any of this. So. That's for that. Now for the cylinder, if you know what the volume of the cylinder is, equals so it's going to be pi r squared times the length of our cylinder. So the length of our cylinder is going to be the minus the diameter of our sphere because we took the 2 halves off. So it's just going to be half of the entirety of the length, which we said earlier was 0.085. And if you do those calculations, your volume of the cylinder comes out to be 0.0048. Everybody got that?
Yep.
All right, awesome. So if
So
you take,
I want to make sure I understand. So like what you collected from your deep knowledge of moles is the length, and then you had to calculate the volume. So you made an assumption about the approximate shape, and then you estimated, okay, they're about, you said about half as wide as they are long.
Yep.
And then this is how you got volume.
Yep.
I think it's great.
Yeah. So a very maybe inadequate estimate, but you know what? That seems about right for the full entirety of the mole to be together 0. Ooh, my math is off again. Give me a second. Zero, 0, 1, 2, 3 meters cubed. So that is the volume of 1 mole, just one of them. And now we have to take the entirety of the volume of 6.022 times 10 to the 23rd of them. That's a little bigger. So with that, so this is going to be our mole planet, the entirety floating in space mass of all of these moles. So if you want to take the volume of this, you're obviously just going to multiply the volume of 1 mole by 1 mole. So the volume of a mole that we just found was 0.0123 times 6.0221409 e to the 23rd. So if you multiply the volume of 1 mole by the amount of 1 mole, you're going to get, well, that didn't work. 7.407 e to the 21st meters cubed. So if you relate that to the volume of Earth, we're about 7 times the size of Earth, is this planet right here. So
Okay.
Earth, planet, you can fit 7 of them inside of it. So the volume is pretty large, but the mass, on the other hand, is going to be a little different. And so for mass, that's again going to be the mass of 1 mole multiplied by the amount of 1 mole. So if you take 6.0221409 e to the 23rd, multiply it by, on the screen, our mass of 1 mole, which is 0.142 kilograms, you're going to get you're going to get 8.55 e to the 22nd kilograms, which, if you see on the screen, is quite a bit less than the mass of Earth, which is because the weight of 1 mole versus the same amount, the same volume of everything that the Earth is made up of. The Earth is just much more dense than this mole planet. You know, a mole planet is not very dense. So that's why we get that big disparity.
Are we assuming incompressible moles, it seems?
Yeah, we're just saying random packing, and they're not going to be squeezed into oblivion. Because, yeah, then we would form like a solid core of solidified mole. And that's just not fun to think about.
Yeah, we don't want to think about that.
So
Mole continents floated on molten
yes,
mole.
which would be bad.
Yes.
So if we look at that, that's going to be the basis for our mole planet, which is where we're going to move into our next portion, which is surface gravity of this planet and pressure at the center of this planet. Now, the pressure, we're going to just assume a lot of things and neglect a lot of things. But the surface gravity, that can actually be pretty accurately measured. So most of our surface gravity, most of our surface gravity is actually just a relationship to what Earth's gravity is. Anytime we talk about other planets, it's usually just a gravitational constant that's in relation to what we have on Earth. So the equation that we use for that is G, which is a gravitational constant, equals the mass of our planet over the radius of our planet squared. And the mass and the radius of our planet are proportional to what Earth's is. So when we take it, our mass is going to be the mass of our planet over the mass of Earth's planet. The radius is going to be radius of our planet over the radius of Earth's planet. So it'll be entirely relational. So when we do this, if we take the mass of Earth, or if we take the mass of our planet and divide it by the mass of Earth, we're going to get a pretty small number. So 0.5. e to the 22nd, and divided by Earth's mass of 5.972 e to the 4th, we're going to get so 0.0143, and that's about 1/30th or so. It's like 1/29 and a half. And then the relationship of our radius.
It is.
So we
that
found
looks like it's about 1/100th.
Maybe I did my math wrong. Yeah, no, sorry, 1/70th. I wrote this down wrong.
Okay.
About 1/70th of what the Earth is. So now that we have the volume of our mole planet, we can find its radius to do the rest of this equation. So if you plug volume into, or if we plug volume into our sphere volume equation, then we can just substitute and find radius. So if we have our volume,
Oh, right, I see.
so we're going to have to multiply our volume by 3/4. So times 0.75, and then we of our planet is going to equal a lot. It's a pretty wide planet. So that's the radius of our planet. And if we take that and we do the same thing with Earth, so what is Earth's volume? 1.6 e to the 21st. Cubed. So we do the same thing. 6. And we're going to get something much, much smaller. And actually, you can look this up, like this is pretty close, but the difference between our Earth's radius all around, they kind of come up with an average of it. So I figured if we're going with a stagnant volume for Earth, we might as well go with whatever the stagnant radius is for it. And this number actually does fall like right within the bounds of what the average radius is. So it's pretty close. So we get R equals e to 6. So quite a bit more. Quite a bit more. So if we divide those two out to find what the relationship is, we're going to get 0.527. So about half, which isn't bad. So if we come back up to our top equation, our gravitational constant for our new planet's gravity is going to be 0.0143 divided by 0.527 squared. And that gives us 0.0514. And that's just a proportionality, so it doesn't actually give us any units to it. But if you wanted to know, that means the gravity on this planet would be 0.04 meters per second squared. So if you weighed 100 pounds on our planet, you would weigh quite a bit less on this planet, like a lot less on this
Like 120, if you weigh like 5 pounds.
Yeah. So it's pretty not dense. And that's the entirety reason for it, is because when you're so far out from, the mass, most of the mass is concentrated on the center of this thing. And with a radius that's that large, you're way out. So it really doesn't have much of an effect. You'll still feel it, like you will be pulled towards this thing, but just a lot less than you would be on Earth. So yeah, that's how much gravity this has. Now, if we want to take that and apply it to the pressure to find what the pressure at the center of this circle is. So in the Earth, we have pretty hefty pressure when you get into the center, but it's not nearly enough to cause any crazy chemical reactions outside of some deep compression. But if we were to take a look right down to the center of this, our pressure would equal 2/3 times pi times the gravitational constant multiplied by the density of our planet squared multiplied by the radius of our planet squared. This number is going to come out huge, and that would make a lot of sense. There's a lot of moles here, and that would definitely happen. So if we do this calculation very slowly, pi times, so we found our gravitational constant before to be 0.504 meters per second squared. And if we multiply it, so the density of this object, obviously density is mass divided by volume. So if we take 8.551 e to the 22nd and divide it by, let's see, 7.407 e to the 21st, square that number, so this is going to be huge, and then multiply it by the radius squared, and we found the radius before. Please tell me I wrote down the radius. I don't want to have to do all that again. I did not write down the radius, so let's see if I have it in here. Oh yeah, there we go. Okay, so that radius, which is enormous, square it. Yep. So the pressure on this would come down to 2.057 e to the 16th pascals. So that's a lot. That's like 10 trillion pascals of pressure. So in our planet, we get to like, I think they said like 100 gigapascals. So this is 100 times more than what our pressure is at the center of our planet. So quite a bit. And again, sketchy math. I don't know what the actual legitimate pressure would be of a mass of moles floating away from each other, because they're not compressed is the issue. Is they're not one solid object. It's a bunch of little small ones. But I'm just assuming if enough of them was like linking arms together in space, that would be the pressure that would be created. Now, if we take this pressure a little further, and this is where it really gets a little iffy, and this is where the science gets fun, but definitely on its accuracy. If we focus in right now on the smallest point in here, we take this small thing to be we look at the center about a 1 meter sphere. We're trying to find how much temperature would be created based on the pressure. So bear with me because this is where it gets a little out there. If you look at the ideal gas law, which I'm going, so it's EV equals nRT. You can see the relationship between volume, pressure, the amount of moles, and temperature using an ideal gas constant. So I looked up how much hydrogen was in a regular human body. And in a 70 kilogram human body, there is a lot of moles. I don't have the actual number, but it's something around 7.04 times 10 to the 23rd molecules of, or 24th molecules of hydrogen in a human body. And so I scaled down the amount that a 70 kilogram person weighs to the amount that a mole weighs, because I assume organic material between animals is similar enough that they would have about the same amount of concentration of hydrogen in them as we do in us. And so with that, I found that in every single mole, like the animal, there is 15.07 moles of hydrogen in every actual little mole. So that would clear up this constant. We know our pressure because we just found it. We know the volume because it's just going to be this 1 meter cube, or 1 meter sphere. And we know a gas constant because that's given. The only thing we don't know is the pressure, or the temperature. So if we take our temperature to be, if we find our temperature, so we're going to take our pressure that we just found, which was the 2.05 e to the 16th pascals. We're going to multiply it by our volume. Our volume is just 1, so it doesn't matter. So I'm going to put my chalk. Okay, so so that's our pressure times our volume. So in 1 meter, in a 1 meter sphere, that's how much pressure is going to be induced on it at the center of this planet. We're going to have, so we're going to take the 15.172 moles, and we're going to multiply it by the amount of moles that we can fit in a 1 meter cube, or a 1 meter sphere. So if you take 1 and divide it by the volume of a mole, of just a regular mole, so 1, and then divide it by the 0.0123. So you're going to get about 81 moles, 81.3 moles that can fit inside of this 1 meter sphere. So that multiplied by 15 to get how many moles of hydrogen would be in that 1 meter cube. So that multiplied by 15.72. So there's going to be 1,278.04 moles in this entire sphere. Okay? We're going to multiply that by our gas constant. So the ideal gas constant is something in chemistry that all ideal gases share, hydrogen being one of those. Again, this is hydrogen that is kept inside of organic material, so I don't know how well that relates to gas constant hydrogen, but we're going to go with it because it's fun. And so our gas constant is 8.314. And that's multiplied by our temperature. So if you multiply those two out, so 1,278.04 multiplied by 8.314, and then we divide our entirety of this by 10,625.69, we are going to get about 1.936 e to the 12th Kelvin, because our ideal gas constant, or our gas law, is in Kelvin. So we're going to get about 193 billion degrees Kelvin. Now, the fun part is that for nuclear fusion to occur, right, you need a temperature only of 100 million Kelvin. So, in essence, what we have done by taking a mole of moles and putting them in space together is a planet 7 times larger than Earth with a gravity that is 1/70th of Earth's, that is now in its core creating nuclear fusion. I don't know
whole
about you
star.
guys, but that sounds awesome.
I'm going to be honest, I don't know if I trust that math.
I'm just the resident genius here. Don't
Hence
don't
it
listen to
being
me.
sketchy math.
There you go.
Yeah.
So that was the talk today. I just wanted to see how far down the rabbit hole we could go in math equations before it got absurd. And when I saw like such a large number, I was like, all right, what happens when you get above that amount of temperature? And the first thing that popped up was like, oh, you need that a ton for nuclear fusion. And I was like, how much? Not as much.
Yeah,
So it was pretty interesting.
that's cool.
Any questions?
What number did you use for your R again?
For the ideal gas constant, it was 8.314.
And that was for hydrogen?
Yeah.
I don't think that's the right number.
What's the ideal gas constant for hydrogen then?
Give me a second.
I assumed it was constant for all ideal gases.
No, there's a different one for each different gas.
Well, it can't be that hard to. Either way.
Wait, is it different?
It's what I have in my book is 4.124.
So actually, we would get about twice this
Yeah.
amount. So, unfortunately, still nuclear fusion ready.
Sure.
So still ridiculous, but slightly less ridiculous.
Yeah,
Or slightly more.
slightly more.
Sorry.
ridiculous.
Slightly more ridiculous.
All right, cool.
So that was my talk for today. I hope everybody enjoyed virtual talk math to me. I think it was solid. I think this works really well, actually.
I enjoyed it a great deal. However, I was disappointed by the lack of snacks.
That's not on the presenter. That is on the administrator here.
I blame Joni.
So if
Yes.
I just brought myself a batch of cookies, that would have been fine.
That would be even worse.
I'm at home. I have a ton of free food now, so like I can't complain.
So,
I have
would-
snacks for me.
well, I was gonna say, should I mail y'all cookies? So they deliver?
Maybe Dr. Kipka, you're the only one that didn't bring snacks for yourself. We all seem to be pretty well fed here.
Yeah. We all have to be careful with our webcams because if you turn the webcam on and there's a wall of toilet paper behind you, everyone's going to be mad at you.
Yeah. That's why Joe's got his off.
That's right. He's in a room full of toilet paper. All right. Well, this was great. Thank you, Joni, and thanks, Josh, for putting it
Yeah.
on.
Definitely.
Alrighty. Well, and then next week, are we gonna see your group?
Yeah, so our Engineering 260 Engineering Research Methods group is going to be presenting our findings for the semester. Little hint, it has to do with underwater reverberation and locating oil. So if you're really into acoustics or you would like to learn a little bit more about acoustics, we'll be diving into it heavily, going into our testing, our results, the few that we could actually get, and future plans for when we do this as a senior research project.
So
Hopefully.
this is related to detecting oil spills under the ice, right?
Yep.
yeah, this is a cool project. I saw some stuff presented on this last spring.
And it's
So-
crazy because like nobody's doing it outside of us. Like there are other ways that people are detecting oil under ice, but nobody's used reverberation. So this is new material.
Yeah, that's cool.
So,
I'm
yeah.
looking forward to it.
so
All right. Well, I will see y'all guys next week, hopefully, and maybe we'll have more than 4 other people joining us. So
We'll see you guys
Sounds good.
soon.
I
you-
guess it is the cookies that get them to come. So
yeah, I thought it was the
I
extra
just
credit.
came
Truly,
to
I
see
did.
moles.
Julie is a true G.
Well, I saw the outline and I'm like, that sounds interesting. I wonder like
Right?
what's going to happen, and I was not disappointed.
There you go.
I mean, that's basically the reason I'm here as well.
Nice, Joe. You saw my last one. You had to see this one.
all right, guys. Well, thank y'all for coming, and I'm gonna stop recording.